In this video, I will discuss some NEET PYQs from the topic gravitation. These questions are based on Kepler's laws of planetary motion. First, I will discuss some basic ideas. Consider mass, say big mass, capital M, and let there be a small mass, say m at a distance. For example, this can be Sun and this can be a planet like Earth. Now, how will this mass move around this bigger mass? Let me assume the bigger mass is at rest. If the mass is given as an initial velocity, say in this direction, gravity force acts along the line joining the two masses. So there is a line joining the center of this mass and this mass. So gravity is an attractive force. So this is the direction of the force due to gravity on the small mass. So this force vector and the initial velocity vector will form a plane, and this mass will move around this mass in that plane. For example, the gravity force is like this, but suppose I give the initial velocity in this direction, then these two vectors will form a plane like this. So the small mass will move in this plane. But here I am considering the case where the initial velocity u is on the plane of this board and the gravity force is also on the plane of the board. So this mass will move around this mass in an orbit like this. So this orbit or a curve is ellipse. So this is by observations made by Kepler, and this is called Kepler's first law. Kepler's first law states that a small mass like planet moving around the bigger mass like Sun moves in an orbit which is in a single plane, and the path is an elliptical path with the big mass as one of the focus. For an ellipse, for example like this is the major axis and this is the minor axis. On the major axis there will be 2 points called the foci. This is the focus 1, this is focus 2. So the big mass should be in one of the focus and the small mass will move in this elliptical path. So this is Kepler's first law. And how will the velocity of this mass keep changing as it moves along the orbit? Here it has got some velocity, and when it comes here, the velocity will have increased. And when it comes nearby, the nearest point, the velocity will be maximum. Here is the velocity at this point. And here will be still more. So how much the velocity changes is given by the condition or rule that the area that is swept by this mass, say in time delta t, the mass moves from here to here. This in time delta t. So the mass will come here. So here, if we join this focus to that point in the orbit, so this is the area that is swept by this planet as it moves around the Sun in a time delta t. If you take the same delta t time here, when it's nearby, it will cover a much farther distance. So this is the arc length covered in the time delta t. Probably can expect it to be like this because here the velocity is more, here the velocity is less, such that the area swept by the planet about the Sun, this area is same as this area. So I call this area as A, which is swept in time delta t, and this area will be the same A because the same time I have taken as delta t. If it is 5 seconds here, the same 5 seconds we take here, this will cover a larger angle because the area covered should be same. This length is more, so even if it covers a little bit angle, it will have some area. To have the same equal area when it is nearby, that is to cover a larger distance. So equal areas is swept by the planet in equal times. This is Kepler's second law. First law states that the path of the planet around the sun is ellipse. Second law states how fast it is moving. It's not uniform. When it's farther away, it will move slow, and it's nearby, it will have the maximum speed. Actually, here the speed is minimum because it's near farthest away. Here is the minimum distance, so this speed is maximum speed. Here will be in between speeds. So this also by again by observation. Now the next is Kepler's third law. So a bigger mass and a small mass will go around the bigger mass in the elliptical path. So let me consider this mass m here and a small mass m here, which is moving in a ellipse like this. The small mass is m here and it's moving like this elliptical path. The same mass can also move in a different elliptical path. Actually, I should make it bigger. Let the mass be mb here and mb here. So this also moves in an elliptical path according to the first law. But this is a bigger ellipse. For an ellipse, from here to here is the major axis. So from the center to this extreme point is the semi-major axis A. So here, from the center to this point, it's again second semi-major axis. We call it A2, and this is A1. Okay, and let the time it takes. See, I can make the planet to go around a bigger ellipse by giving a appropriate initial velocity. So here the initial velocity u, we have some value u1. Here the initial velocity will be a different value u2. Okay, so depending on the initial condition, the size of the ellipse will be decided. But the interesting thing is the time that it take to go around the path once, it's called the time period t1, because after it's going to repeat. Here is the time period for this planet to go around this bigger mass of the sun, let it be t2. Now the question is, suppose let me take the case where I have doubled this semi-major axis as I have doubled this size of the ellipse, where the semi-major axis is twice the first case. Then how will be t2 related to t1? We can expect this t2 to be greater than t1, but by how much? So it follows the relation t2 by t1 square equal to a2 by a1 cube. This also by observations made by Kepler. So in this particular case where the size of the ellipse has doubled, it will be 2 cube, which is 8. So t2 is square root of 8 into t1, which is 2 root 2 times t1. So when the size of the ellipse is doubling, the time period is going up by 2 into root 2 times. Root 2 is 1.414. So this is approximately 2.828. So when the size of the ellipse is doubling, the period is going up by approximately 3 times or 2.8 times. This is Kepler's third law. This is also again by observations. Few more basic concepts before going to the questions. Again, let me take the system of big mass and small mass. The force between them is the gravitational force. And since the small mass is moving, it will have a velocity, some velocity, system of big mass and a small mass m moving some velocity v. So what is the energy of the system? Let me assume this thing is at rest, or I can attach my frame to this one. So with respect to that frame, this mass is at rest. So the energy of the system is half m v square. In addition to this, in general, a physical system can have one more energy, which is potential energy. Here in this case, gravitation potential energy. One more basic concept of is work done on the system will increase the potential energy. Work done by the system, here the system is the system of these two masses, will decrease its energy. Here in this case, potential energy. Obviously, if the system is doing work, it loses energy. If work is done on the system, its energy is increasing. An example of this one is, say this is Earth's surface, and the mass is here initially, and I'm raising the height of this mass to this height, say h. So to do this thing, this is the initial state, and this is the final state. So to do this, I have to do some work. I have to lift this mass and keep it in its height. So here work is done on the system, which is equal to force into resistance. Force is weight, mg, which will pull it down. So to overcome that force and raise the height by h. So this is the increase the potential energy in this case. Another example of this work done on the system, increase the potential energy is, suppose I have a spring. One side is fixed. If it's in a relaxed state, and after that I'm trying to, say, stretch the spring. This is the initial state. It's a relaxed position. Now if I try to stretch this spring by applying a force, I can have to do work on the system. This is the final state. So again, work is done on the system, which is integral f ds, and force exerted by a spring is k into x, and ds is dx. If you choose x-axis towards right, integral. So this will come out to be half k x square, which is the energy stored in the spring, which is the potential energy of the system. So here also I'm doing work to stretch the spring, which is getting stored in the system as potential energy. Similarly, if I compress the spring by x, again I have to do the same work. So basically I want to convey that if work is done on the system, potential of the system will increase. If the system does work, it will lose energy, potential energy. So from this we can get a understanding of the formula for potential energy of a gravitation system. This is a mass m, capital M, and say initially the small mass m is at infinite distance and the velocity will be 0. So as the force is acting on this mass towards this bigger mass, it will move towards this mass and will come here. Okay, so this is the initial state of the system, and there is a final state where the distance has decreased. So to go from the initial state to the final state, should work be done on the system. Without any external force acting on this system, the mass will automatically move because of the attractive force. So there is no work done on the system. But for the system to move slowly from here to here, I have to apply a force in this direction, if external, so that the mass moves slowly. The velocity of the mass at any point should be very, very small, approximately 0. because I want only one form of energy to appear in the system, which is the potential energy. If this mass is moving fast, then there will be kinetic energy in the system, which I don't want. So that I can make this condition satisfied by applying external force, which is equal to the force which is pulling this mass, which is the gravity force. So the work done here, the work is actually done by the system because the system is actually pulling the mass towards this one. So work done on the system is integral f external dot ds. This infinite to this say distances r, infinity to r. F external is on this one, it's towards right because I have to apply this force to reduce the speed of this mass. Just like a brake applied to your vehicle, you have to reduce the speed so that the velocity at any instant is very, very small, so that the kinetic energy of the system is zero. So the external force towards right, the displacement is towards left, so F dot ds is negative, and this force on this one, which is the gravity force, gmm by r square at this distance r into dr. D is actually minus dr because r is from here to outside. Direction of r is this is the direction of r cap. So ds is minus dr, and f dot ds will have a negative sign because f and ds are in opposite directions, and you have to integrate this one. So this is nothing but integral of gmm is constant dr by r square, and I'll choose a convenient reference that potential energy of this initial system when the mass is in infinity is zero. So the work done on the system is the increase in the potential energy, which is potential energy when it is at infinite distance minus the potential energy when it is at r. So this one is dr by r minus 1 by r. Integral of 1 by r square is minus 1 by r between the limits infinity to r. So this will become gmm by r, and this is minus ur. So from this I'll get expression for the potential energy when the system, when the smallest distance r is minus gmm by r. So potential with the mass is at an infinite distance is zero. After that it becomes negative. So here it is more negative. Here it is less negative. Because as a r is smaller, this thing will become larger value. So because the next will become more negative. So as the distance between the mass decreases, the potential of the system is decreasing because it's becoming more negative. So obviously you can expect the potential of this system is less compared to this one because from here if I release this mass, it will reach a higher velocity here. If I release this mass from this position, it will reach a lesser velocity here. So energy of this system is less compared to energy of this system. So that's why you need this negative sign in this formula. So with this understanding, you can solve this NEET PYQs. Timestamps are given in the description box. You can watch parts of video if you're running short of time. I'll discuss some 7 questions. This is the first one. Kepler's third law states that the square of period of revolution t of a planet around the sun is proportional to the third power of the average distance r between sun and the planet. That is t square is k into r cube. Here k is constant. If the masses of sun and planet are capital and small n respectively, as per Newton's laws of gravitational force of attraction between them is F equal to gmm by r square. Here g is gravitational constant. The relation between g and k is described as. You can pause and run this question. So the time period, let me consider the case of circular orbit. See, in general, the mass is here, and this planet M can go in a elliptical path. Circle is special form of ellipse. Special case of ellipse is a circle where the two foci will meet. So I can also consider the case where M is at the center of the circle and this small m is moving in a circle. So this is circle, that is ellipse. So this should be true even for a circular path. So in this circular path, the time period t is the circumference 2 pi r by v. Okay, and also force has to be in balance. So this is the gravity force, and there is a centrifugal force. So the gravity force is given by Newton laws of gravitation, gmm by r square. That should be balanced by the centrifugal force mv square by r. So that will give v as square root of gm. So here I need t square. Actually, I need v. So if I do t square on both the sides, I'll get t square as 4 pi square r square by v square. V square is nothing but gm from here. I don't need this. V square will have is gm. So this is t square, and this is equal to, according to Kepler's law, it's equal to k into r cube. Here there is a mistake. This is r square. So we'll have, and then this r will go. So v square by r an expression. Or I can write v square as gm by r. So v square is gm by r. So we'll have 1 r here. So we'll cancel this r fully. So from this I'll get gmk equal to 4 pi square. So option E is the correct answer. Gravity with gm by r square, that's equal to centrifugal force. Option is the correct answer. I consider circular case, simple case of circular orbit. So the force, gravitational force is balanced with centrifugal force. So gm by r square equal to mv square by r. So from there I'll get the velocity as square root of gm by r. And time period t is for a circular path is 2 pi r by circumference by velocity. So 2 pi r by v. V is this one, square root of gm into r, half is there. So it will become r3 by 2. So if I square on both this, I'll get t square as 4 pi square by gm into r cube. So comparing this with t square equal to k into r cube, k is 4 pi square by gm. From this I'll get gm into k as 4 pi square, which is option A. So this is the next question. The kinetic of a planet in an elliptical orbit about the sun at positions A, B and C are Ka, Kb and Kc respectively. AC is the major axis and SP is perpendicular to AC at the position of the sun as shown in the figure. Then kinetic of A is less than B, less than C, and different relation. So basically, you have to find the kinetic energies at positions A, B, and C, and relate them. Which one is small, which one is big. Okay, now in this question, so according to Kepler's second law, equal areas are swept in equal amount of time. So here, since the distance is large, the velocity will be smaller. Here the distance is smaller, so velocity would have increased, and here the velocity will be maximum. Minimum velocity, maximum velocity, this in between velocity. So velocity at point A is more, so kinetic at point A will be maximum, and kinetic at point C will be minimum, and kinetic at point B will be somewhere in between. So this is the maximum value. So K is greater than KB, which is greater than KC. So it's basically based on Kepler's second law, which says equal areas are swept in equal amount of time. Since this length is more, it has to sweep a smaller angle to have the same area. So here it has to move slow. Here it's coming a little bit near, so it will cover a larger angle. Here it's minimum distance, so it will cover a large maximum angle. So here the velocity has to be more, maximum. Equal areas are swept in equal amount of time. This is Kepler's second law. So farther away from focus, the planet moves slowly. So velocity is maximum is nearby, which is at A, and minimum at farther away, which is B. So option B is the correct one. This is the next question. A planet is moving in an elliptical orbit, is closest to the Sun at a distance r1, farthest away at distance r2. v1 and v2 are linear velocities at these points respectively, then the ratio v1 by v2 is. You can pause it on this question. So this is the big mass and the planet small mass. So go to elliptical path according to Kepler's first law. This is the maximum distance. From here to here, farthest away at this. So this distance is r2. This is the minimum distance when it is here, r1. This is r1. This is maximum distance r2. Okay. So the gravitational force is this way, velocity is this way. So this system will have an angular momentum, which is r cross p. At this position, velocity will be like this. So r and b are perpendicular. So L at this position, L2 is r2 into mass into velocity at point 2. So with the angular velocity system at point 1, L1, r1 r cross p r1 into m into v1. Angular momentum will be conserved if there is no external torque acting on the system. There is no external force or torque acting on this one. The only force is the interaction force. So torque, angular momentum will be conserved because external torque is 0. So these two will be equal. So that means R2 V2 equal to R1 V1. So V1 by V2 is R2 by R1. B is the correct answer. Angular momentum of a system is R cross P. So this is the path of the planet around this sun. So at this point, the angular momentum system is R cross P, which is R2 into mv2. At this point, the angular momentum system is R into mv1, R1 mv1. So from this I get the ratio as R2 by R1. Angular momentum is conserved because there is no external torque acting on the system. This is the next question. The figure shows elliptical orbit of a planet about Sun. The shaded area SED is twice the shaded area SAB. If T1 is the time for the planet to move around from C to D and T2 is the time to move from A to B, then T1 is 4T2, T1 is 2T2. Now relate T1 and T2. You can pause and run this question. So this area SCD is twice the area SAB. So if area is moving, the amount of time is more. So the time to go from C to D will be twice the time to go from A to B. Because if the time was equal from here to here, the area should be equal. Since this area is twice this one, the amount of time it takes to go from here to here will be twice. Because area is pushed into the time. So T1 is the time planned to move from C to D. So this is T1. And T2 is the time to move from A to B. So 2, T2. So T1 equal to 2T2. B is the correct answer. So equal area is separate equal number of time. So area is proportional to the time. If time is more means it will sweep more area. This is Kepler's second law. So area to go from C to D is twice the area it covers when going from A to B. This is given in the question. So area is proportional to time. So time to go from C to D will be twice the time to go from A to B. Let's move to the next question. The time period of revolution of planet A around the Sun is 8 times that of B. The distance of A from the Sun is how many times greater than that of B from the Sun? You can pause on this question. So Sun is here, and then planet A. Okay, the time period of revolution of planet A around the Sun is 8 times. So this from the Kepler's third law, we know T square is proportional to A cube. A is the semi-major axis of the ellipse. So larger time means it's farther away. So since A is taking more time, it's farther away. So planet B will be somewhere here. Both are making elliptical paths. Since A is taking larger time, it will go on a bigger ellipse because A should be more. So this we can use for A and B. So TA square by TB square should be equal to A for the planet A cube by semi-major axis of the planet B cube. This is Kepler's third law. And TA by TB is 8 square. TA by TB is 8 square equal to size of the ellipse of planet A cube. 8 square is 64. 64 can also be written as 4 cube. 4 into 4 is 16. 16 into 4 is 64. So that means 4 equal to, so the size of the ellipse of planet A is 4 times bigger compared to size of the ellipse of planet B. So how many times the A is greater than B? So it's 4. A will make a bigger ellipse because it takes more time to go around the Sun, and it's 4 times more because the period is 8 times more. A is the correct option. The time period of planet A is 8 times more compared to planet B. So if I square this one, I'll get TA square as 64 times TB square. And Kepler's third law says the period square is proportional to the R cube. So I can write instead of T square, R cube. So T square can be replaced by R cube. So from this I'll get RA is 4 times RB. This is the next question. The distance of two planets from the Sun are 10 raised to 13 and 10 raised to 12 meter. The ratio of time periods of the planets is. This is a simple question. Sun is there, and then two planets. First planet is at 10 larger distance. So planet 1 is here, 10 raised to 13, and planet 2 is nearby, 10 raised to 12 meters. Okay. So I have to use the Kepler's third law. T square is proportional to A cube. So 1 is farther away. So T1 by T2 whole square equal to A1 by A2 cube. A1 is this distance. So this ratio is 10. So 10 cube. So the ratio of time periods T1 by T2 is, I have to take square root of this one. So this is nothing but 10 square into 10. So root of 10 square is 10 and root of 10 is 10. So it's 10 root 10. Kepler's third law, time period is, square of the time period is proportional to the A cube. So R1 by R2 is given as 10 in this question. From this I get the ratio of the time period as 10 root 10. This is the next question. A planet is moving in an elliptical orbit around the Sun. If T, E, V, E and L stand respectively for kinetic energy, gravitational potential energy, total energy and magnitude of angular momentum about the center of force, which of the following is correct? T is conserved. T is kinetic energy is conserved. V, gravitational potential is always positive. E is always negative. L is conserved by the direction of the vector. L changes continuously. So option A, T is kinetic energy. Kinetic energy is conserved means not changing, which is not true because the elliptical orbit, here the velocity will be minimum, here the velocity will be maximum because here is to sweep equal areas equal in water. So this is the Sun. So kinetic energy will be minimum here, maximum here. So A is not true. V is potential energy, gravitational potential energy, which is given as minus gmm by r. Here the reference is potential energy at infinity is 0. Potential energy at infinite distance or the infinite separation is 0. This is by assumption. With this assumption, it's always negative. So this is not true. It's always negative. E, total energy. Total energy is potential energy plus kinetic energy. Potential energy is minus gm by r. Can is half mv square, where v is the orbital speed. This orbital speed we can get from equating the force to the centrifugal force. So if you do this, the standard formula is minus half gmm by r. So it's always negative. So C is true. Angular momentum of the system, there is no external force acting on the system, so there is no external torque on the system. So angular momentum L is conserved. Option D, L is conserved, and L is a vector. That means both the magnitude and the direction of the angle both are conserved. Here it says L is conserved, but the direction of the vector changes continuously. This is not true. Direction also is conserved. Direction also is same. Actually, here the suppose this is this one. So r cross p, r is if you take this as r, so r cross p, this is r vector, this is p. So r cross p is out of the plane of the board. So everywhere the direction of L vector is out of the plane of the board. So direction of L is also conserved. So direction change is conserved. This is not true. It does not change. So only correct option is option C. So this is what I explained here. Kinetic is half m v square. They are represented as t in this question. So farther away, velocity is small because Kepler's second law, equal area should be swept in equal number of time. So farther away should be small. So kinetic will change. It's not constant. But in the case of special case where the path is circular path, then in that case v is same because the distance is always same. So in that case the kinetic will be same. But here it's a not a circular path, it's elliptical path. So kinetic is not conserved. Potential energy is minus gmm by r. The symbol they use is v. So here it's negative, always negative. This is with the assumption that the potential at infinity is 0. Total energy is kinetic energy. So this one gmm by r. So using this force balance, I can eliminate v. Using that expression for v from here, I'll get the expression of total energy is minus half. So total energy is always negative. So C is correct. Option C. Option D, L is conserved because there is no external force or torque acting on the system. So angular momentum is a vector. Both the direction and the magnitude are conserved. So D is not true.